Hello, my dear students. Welcome to my class. I think all of you are good in health. Today, we will start a new chapter of class 11 mathematics. So, the chapter name is Principle of Mathematical Induction. This is the fourth chapter in your book. So, this chapter is very easy. Okay. So, if you understand what is principle of mathematical induction, how to use this method, then you can easily solve the problems. Okay, so let's see the statement of principle of mathematical induction. Now, statement, the principle of mathematical induction. Okay, suppose there is a given statement Pn involving the natural number n such that the statement is true for n equals to 1, that is P of 1 is true. Okay, and if the statement is true for n equals to k, where k is some positive integer, then the statement is also true for n equals to k plus 1. That is, truth of pk implies the truth of pk plus 1. Clear? So first statement is, if the test statement is true for n equals to 1, okay, that is p of 1 is true. And second one is, if the statement is true for n equals to k, then the statement is also true for n equals to k plus 1. Clear? Then Pn is true for all natural numbers n. Clear? So this is the main things of the principle of mathematical induction. Now note, property 1 is simplify a statement of fact. There may be situation when a statement is true for all n greater equals to 4. If the statement is true for all n greater equals to 4, in this case step 1 will be starts from n equal to 4, and we shall verify the result for n equals to 4, that is P4. Clear? Next property 2 is a conditional property. It does not assert that the given statement is true for n equals to k, but only that if it is true for n equals to k, then it is also true for n equals to k plus 1. That means if the statement is true for n equals to k, then it also true for n equals to k plus 1. So to prove that the property holds, only prove that conditional proposition. Okay, so if that statement is true for n equals to k, then it also true for n equals to k plus 1. Clear? Now main thing is, this is the principle of mathematical induction. Okay, if the values of n greater equals to 1, then at first we check for the result is true for n equals to 1 or not. If the values of n greater equals to 2 or greater equals to 3 or greater equals to 4, then we check the result is true for n equals to 2 or n equals to 3 or n equals to 4. Clear? Now students, what is the meaning of conditional property? Listen, if we write Ram is a man. Okay, next, all men are mortal. Okay, see, then Ram is also mortal. Clear? That's mean if condition A and condition B are true, then C established. That's mean if, since Ram is a man and all men are mortal, then definitely Ram is also mortal. That's mean if condition A and condition B are true, then C established. Similarly, if P of K is true, then P of K plus 1 is also true. Clear? So, if Pk is true, then Pk plus 1 is also true. This is the conditional property. Clear? But the main thing is this. This is the principle of mathematical induction. Okay. Now, see an example how to solve the problems using principle of mathematical induction. Okay. So, tell me the formula of sum of n natural numbers. Suppose 1, 2, 3 dot dot n. Okay. So, here n natural numbers 1, 2, 3 dot 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 n. So, sum of n natural number means 1 plus 2 plus 3 plus dot dot n. So, what is the formula of sum of n natural number? Tell me. So, sum of n natural numbers, that's mean 1 plus 2 plus 3 plus dot dot plus n equals to n into n plus 1 divided by 2. Okay. So, this is the formula of sum of n natural numbers. Clear? Now, we prove this statement using principle of mathematical induction. Clear? So, let's see solution. Let Pn be the given statement. That is Pn such that 1 plus 2 plus 3 plus dot dot plus n equals to n into n plus 1 whole divided by 2. Clear? So, next is we check this result is true or not for n equals to 1. So, for n equals to 1, left hand side equal to, listen, this is the left hand side and this is the right hand side. So, if we put n equals to 1, that's mean 1, that's mean only first term, so 1, and right hand side equals to 1 into 1 plus 1 divided by 2, that's mean 2 by 2, so equals to 1. So, left hand side equal to right hand side. Clear? So, P of 1 is true. P of 1 is true. So, the condition 1 is satisfied. So, after condition 1, now we prove that the condition 2 or property 2. That's mean we assume that Pk is true for some integer k, and after that we shall prove Pk plus 1 is also true. Now let's see. So this is for condition 2. Okay. So let us assume that pk is true for some integer k. Okay, so let us assume that pk is true for some integer k, that is pk such that 1 plus 2 plus 3 plus dot dot k equal to k into k plus 1 whole divided by 2. Okay, now we shall prove that pk plus 1 is also true. Okay, that's mean we prove that, or that is we shall prove that p k plus 1 such that 1 plus 2 plus 3 plus dot dot k plus 1. Okay, here we put k plus 1 in the place of k, that's why we shall prove pk plus 1 such that 1 plus 2 plus 3 plus dot 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 plus k plus 1 equal to, here also this is k plus 1 into this is k plus 1 plus 1 whole divided by 2. Okay, next we have 1 plus 2 plus 3 plus dot dot k plus 1. That's mean here we retain the left hand side of pk plus 1. Clear? So that's why we have 1 plus 2 plus 3 plus dot dot plus k plus 1. Now student, see that first term is 1 and second term is 2, third term is 3, similarly fourth term is 4, and the last term, that's mean k plus 1th term is k plus 1. So if we add 1 with first term, then we get the second term, that's mean 2, then 2 plus 1, that's mean third term, 3 plus 1 equals to 4, that's mean fourth term, or inversely 3 minus 1, that's mean 2, second term, 2 minus 1, that's mean 1, first term. Clear? So in next line, equal to 1 plus 2 plus 3 plus 4 plus dot dot plus, and last term is k plus 1. Listen, 4 minus 1 3, third term, 3 minus 1 2, second term, 2 minus 1 1, first term. So this is the last term, k plus 1. So previous term of k plus 1 is, that's mean k plus 1 minus 1, k plus 1 minus 1. So plus 1 minus 1 cancel, simply k. So equal to 1 plus 2 plus 3 plus 4 plus k, and last term is k plus 1. Now student, we already assume that 1 plus 2 plus 3 plus dot 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 k equal to, result is k into k plus 1 divided by 2. That's mean up to 1 plus 2 plus 3 plus 4 plus dot 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 plus k, this equal to k into k plus 1 whole divided by 2, and the remaining term is k plus 1. Clear? Because we assume that pk is true, that's why pk such that 1 plus 2 plus 3 plus dot 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 plus k equal to k into k plus 1 divided by 2. So that's why 1 plus 2 plus 3 plus dot 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 k plus k result is k into k plus 1 divided by 2, and the last term is k plus 1. Clear? So in next line, if we common k plus 1, then from the first term here is k by 2, and here this is 1. Clear? So finally we got k plus 1 into k by 2 plus 1 in third bracket. Okay. Next, if we simplify this, then we get equal to k plus 1, and in third bracket k by 2 plus 1, so equal to, this is k plus 1, here LCM is 2, that's mean k plus 2 divided by 2, so equal to k plus 1 into k plus 2 whole divided by 2, so equal to k plus 1 in second bracket k plus 1 plus 1, because k plus 2 can be written as in this form, k plus 1 plus 1 whole divided by 2, and this equal to p k plus 1. Clear? That's been right hand side. So next we can write p k plus 1 is true when pk is true. pk is true. Clear? So pk plus 1 is true when pk is true, or whenever pk is true. Clear? And the last line is hence from principle of mathematical induction, the result or the statement is true for all natural number n, for all natural number n. Clear? Why for all natural number n? Because the given statement is true for n equals to 1. After that we assume that the result is true for n equals to k, and finally we prove that the result is true for n equals to k plus 1 also. That's why the result is true for all natural number n. Clear? So you write in this form. So pk plus 1 is true when pk is true. Hence, from principle of mathematical induction, the result is true for all natural number n. Complete. Okay. Now students, see this problem. Example 1. For all n greater equals to 1, prove that 1 square plus 2 square plus 3 square plus 4 square plus dot 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 plus n square equal to n into n plus 1 into 2n plus 1 whole divided by 6. Listen, previous one was sum of n natural number and this one is sum of square of n natural number. Clear? Previous one sum of n natural number, but this one sum of square of n natural number. Clear? So sum of square of n natural number equal to n into n plus 1 into 2n plus 1 whole divided by 6. Okay, that's mean now we prove this statement using principle of mathematical induction. Same language. So solution, let the given statement be Pn, that is Pn such that 1 square plus 2 square plus 3 square plus 4 square plus dot 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 n square equal to n into n plus 1 into 2n plus 1 whole divided by 6. So next, for n equals to 1, that's mean p of 1 such that if we put n equals to 1 in this left hand side, that's mean 1 square, that's mean only first term, so 1 square equal to 1, this is the left hand side. And if we put n equals to 1 in right hand side, that's mean 1 into 1 plus 1 in bracket 2 into 1 plus 1 divided by 6, that's mean 1 into 2 into 3 whole divided by 6, that's mean 6 by 6 again 1. So left hand side equals to 1 and right hand side is also 1, so which is true, that's mean p of 1 is true. Okay, next, so condition 1 or property 1 complete, satisfied. Next, condition 2. So let us assume that pk is true for some integer k. Okay, that's mean pk such that 1 square plus 2 square plus 3 square plus 4 square plus dot 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 k square equal to k into k plus 1 into 2k plus 1 whole divided by 6. Okay, because we assume that pk is true for some integer k, that's why pk such that 1 square plus 2 square plus 3 square plus dot 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 k square equal to k into k plus 1 into 2k plus 1 whole divided by 6. Now we shall prove that pk plus 1 is also true. Okay, so we shall prove that pk plus 1 is also true. Now we have 1 square plus 2 square plus 3 square plus 4 square plus, at first you write this line 1 square plus 2 square plus 3 square plus 4 square plus dot 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 up to this k plus 1 whole square. In next line you just write 1 square plus 2 square plus 3 square plus dot 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 plus k square and last term is k plus 1 whole square. Okay, listen, same things, 4 minus 1, that's mean 3 square, 3 minus 1 2 square, 2 minus 1 1, that's mean 1 square. Clear? So that's why k plus 1 a whole square, last term is k plus 1 a whole square in pk plus 1. Okay, and previous term of k plus 1 whole square is k plus 1 minus 1 whole square. So plus 1 minus 1 cancel, that's mean k square. That's why in second line we retain 1 square plus 2 square plus 3 square plus dot 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 plus k square plus k plus 1 whole square. Clear? So at first you write these things 1 square plus 2 square plus 3 square plus dot 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 plus k plus 1 whole square. If last term is k plus 1 whole square, then previous term k plus 1 minus 1, that's mean plus 1 minus 1 cancel, so only k square. Clear? So in second line you write this, after that 1 square to up to k square is true. That's why we can write we can write k into k plus 1 into 2k plus 1 whole divided by 6, because we assume that pk is true. That's why we written this, and last term is k plus 1 whole square. So if we LCM 6, then k into k plus 1 and 2k plus 1 plus 6 into cross multiply 6 into k plus 1 whole square. After that, if we common k plus 1, then after simplification 2k square plus 7k plus 6 whole divided by 6, simple things. Here we common k plus 1. Okay, third bracket from this k into 2k plus 1, and from second term plus 6 into k plus 1 whole divided by 6. So after simplification you got these things. Okay, you get these things, k plus 1 into 2k square plus 7k plus 6 whole divided by 6. Next, if we middle term these things, that's mean 2k square plus 7k plus 6, then we get k plus 1 into k plus 2 into 2k plus 3. Okay, after this is k plus 1, this is k plus 2 and 2k plus 3 whole divided by 6. After that, k plus 1 and this k plus 2 can be written as k plus 1 plus 1, and this 2k plus 3, that's mean 2 into k plus 1, that's mean 2k plus 2 and plus 1 whole divided by 6. Clear? That's mean this equal to p k plus 1 right hand side. So thus pk plus 1 is true whenever pk is true. Hence, from the principle of mathematical induction, the statement pn is true, or the given statement is true for all natural number n. Clear? Same language. Okay student, I think everything is clear. Okay, now students, homework. Example 3 and exercise 4.1 question number 2. Okay, these two problems are homework. Example 3 and exercise 4.3 question number 2. Okay, so student, now today's session is complete. I think this class was helpful to you, and if you have any queries you can ask me. I think you have understood the things. Okay student, thank you. Stay safe, stay at home.